Okay, let's get started here. So, of course, today is our last regularly scheduled class. Our final exam is Tuesday of next week at 10 a.m. Are there any questions?
Yeah. What are the underlying assumptions on multinomial regression?
Well, let's think about that. First of all, you have a multinomial distribution. Okay.
Multivariate normal?
No multivariate normal. I would in fact characterize this to have less assumptions than, let's say, a discriminant analysis. The reason being is because a multinomial is rather natural because you have you have J categories, just like how a binomial or a Bernoulli distribution would be natural in a situation where you have just two possible outcomes. Still with that though, you could encounter situations, if you've ever heard of the case of over-dispersion, you could encounter that even in this kind of a setting here, and there are ways to handle that similar to if you've seen it in like logistic regression or Poisson regression where it's a big issue there. So overall, I would say that this has less assumptions, but it still does have some assumptions. Another overall assumption is that we do have this this parametric, how should I say? Let me put it a different way. We have this, you saw that plot of, let's say, pi versus x. We have this nice little curve there. Well, that is an assumption, and there are probably more how should I say, there are other ways out there to get around having just a nice curve to that plot. One could perhaps incorporate that into an analysis as well. So I guess those are the overall assumptions that I see. So does that answer your question?
Yeah.
One of the nice things too is that you're not necessarily making assumptions about your x's. Where in a discriminant analysis setting, you're essentially saying x has a multivariate normal distribution. And so especially if you have, let's say, qualitative variables as your x's, well, there goes the assumption. Where with multinomial regression or logistic regression, no big deal. Are there other questions? Okay. So we just have a few more pages to cover in this multinomial regression set of notes. So obviously we spent a lot of time on the logistic regression section on ROC curves. So you might be thinking, well, is there some kind of natural extension to ROC curves here for when you have, let's say, J greater than 2 categories for your data? Well, there are extensions, but it's not necessarily as clear-cut about how to approach the problem as it was with logistic regression. So with logistic regression, you only have 2 possible categories. Thus, that led to having a sensitivity, led to having a specificity. Well, obviously, if you have J categories, think of the case of 3, well, you can't just necessarily define that sensitivity and specificity because now you have, let's say, 3 different ways to be correct in your classification. Also, think of all the different kinds of errors now that you could potentially have, too, when you have greater than 2 categories. It's not necessarily just a false positive rate that you're interested in and a false negative rate. Here, you have a lot more possibilities for classification errors. Well, because of that, then this research area is definitely not as well developed with respect to multinomial regression. And there are some references out there on it. In particular, I'll point you to this 2008 biostatistics paper that provides a nice little review of it if you're interested in learning more about it on your own. Okay, so what about variable selection? Well, we have the same issues with variable selection here as we have had with other classification methods that we talked about. These variable selection methods do not take into account necessarily the overall correct classification rate. And that's our primary goal with using these models, is to maximize that overall correct classification rate. There are many other types of regression models out there that allow you to model a multinomial response. What we've talked about is the most basic model, and to some respect the most used model. But in particular, I do want to bring up one other possible model. For those of you who've had me for Set 875, you've seen this model before. It's called a proportional odds model. It's used in situations where now your categories that a particular observation could fall into, in terms of, for us, would be populations, the categories are ordered in some way. A classic setting where this occurs, and I brought this up last time, is that let's say that you have a response to a survey or a survey question, and it's measured on a Likert scale. So, for example, Category 1 could be very dissatisfied. Category 2 could be dissatisfied. Category 3 could be neutral. Category 4 would be satisfying. Category 5 would be very satisfied. So you can see kind of an ordering there. And, if you have that ordering, it would be nice if you can maybe somehow take that into account. And if you take it into account, perhaps then you could come up with a better model and thus a better classification, better classifications. So with a proportional odds model, what we look at is this. We look at the probability of y, where y is which category is being chosen. Probability y is less or equal to j. So now, instead of focusing simply on the probability y is equal to j, now we're going to focus on a cumulative probability. And that makes sense when you have this ordering of the categories. So you might be interested in, well, what's the probability that you are, let's say, less than or equal to neutral on your response on a Likert scale. With that, we can set up then what looks very similar to a logistic regression model in terms of now we're going to model the logit of the probability of y less or equal to j. In other words, the log of probability y is less or equal to j divided by 1 minus the probability y is less or equal to j. So that looks very similar to what we saw with a logistic regression model before. Obviously, the difference is that you're modeling cumulative probability. On the right side, then, we have what we kind of a combination of what we saw with a logistic regression model and a multinomial regression model. First of all, just like with the multinomial regression model, notice this intercept-like parameter, beta sub j 0, changes as a function of j. But then on the right-hand side there, we only have we have a linear combination of the betas with the x's, but notice you do not see any j's there. And without getting into all the reasoning behind that, it helps to take advantage of the fact that you do have this ordering in the categories. If you want to know more about that, take my Set 875 class. There are still a few spots open. Now with this then set up for our model, we can come up with, well, what would be just pi sub j itself. And it's just a matter of going through some algebra. Here's pi 1, here's pi sub capital J, and then for little j somewhere greater than 1 or less than j, we get that as our actual probabilities for a particular category. So with that then, as you might expect, we would estimate the model, put in the beta hats in there, so we get pi hats for every single observation, and you classify the observation into the category or the corresponding population for which the pi hat is the largest. Not too difficult. So I thought I'd try that with our weak data. Perhaps this is somewhat questionable, but I thought, well, maybe I could say scab is less than sprout is less than healthy. What would happen? It doesn't hurt to just to try it. So I estimated the model. The corresponding code of how to do that is in my program there. I estimated the model. I used my summarize.class function with this. And I got about 69% of the scabs correct, 50% of the sprout, 71% of the healthy. Overall correct classification rate, about 63%. And this is a little bit lower than what we had previously. On a test, I'm not going to ask you to estimate one of these models. I just wanted to bring this up that there are other possibilities out there. Okay, so I believe then that concludes multinomial regression. Any questions? Okay, next, let's briefly, very briefly, talk about the testing means section, which we did not do. I'm not necessarily disappointed that we didn't do it. This is a traditional section that will be taught in a multivariate course. I have always taught it in the past, just using SAS. But as things change over time in terms of what are the most important topics to cover in one class, I believe now that this is now towards the end of the what are important topics to talk about. In terms of if it was a topic that we didn't get to, I wouldn't be disappointed. But I do at least want to spend, I don't know, maybe at most 5 minutes just briefly say what this section was, so that after you get done with this class, let's say on Wednesday, next Wednesday, you can take out these notes and read them. A lot of this stuff is direct extensions to the stuff you learned in your very first STAT course, where you learned about a t-test for a mean. So in that setting then, you looked at hypotheses such as this. The mean is equal to some constant, let's call it mu sub 0. That's the null hypothesis. The alternative hypothesis, not equal. It's probably the very first hypothesis test you've ever saw, and you could use a t-test statistic to do this particular test. Well, what happens then if instead of just having one mean in that null hypothesis, an alternative hypothesis, how about we have a vector of means? And that's what this testing means section is basically centered around. So now notice that these mu's are bolded. So now you have a vector of means. Let's say a p by 1 vector. One then can use what's called Hotelling's t-square statistic to come up with a test statistic to test this hypothesis, or test this null hypothesis. Interestingly, if let's say p was equal to 1, meaning you only really had one mean, this Hotelling's t-square ends up being exactly the same, well, I guess the square of what you would use for a regular old t-test. So that's kind of cool that that happens. Now, in order then to derive a distribution under the null hypothesis for Hotelling's t-squared, you do have to make some assumptions, just very similar to what you would do when you're testing one mean. And you have to say your data comes from a multivariate normal distribution here. And then through using a little transformation of t-squared, you can compare it actually to an F distribution to make a judgment of do you reject or don't reject. And so I give some examples of how to do that. I'll let you look at that on your own if you have interest. Now, there are settings where you might be interested in not just testing, is a mean vector equal to some set of constants? You might be interested in looking at linear combinations of the means in your mean vector to determine if they are equal to something else. So, for example, imagine a situation where you have 3 treatments. So hopefully this terminology should sound familiar to you from a STAT 801 and 802 setting. You have 3 treatments, and you want to know if the treatment means are all equal to one another. Well, in that particular setting, what you could do is test. is mu1 minus mu2 equal to 0? And is mu1 minus mu3 equal to 0? Of course, then that implies that mu2 minus mu3 will be equal to 0 as well. Just go through the algebra. And so what you might be interested in is these linear combinations of the mean vector, and do a hypothesis test involving that. In terms of matrix algebra then, that means applying this little matrix of, using again some terminology you should have heard before, using this matrix of contrasts. Apply this matrix then to your mean vector and you get the linear combinations you need. So in general we could call this matrix H. So now our hypothesis test then looks something like this. The null hypothesis is H times mu is equal to a vector of constants, we'll just call it little h, versus then the alternative hypothesis is not equal. One could do a simple extension to Hotelling's t-squared statistic. And basically it's the same statistic that we saw before, but now you have some h's in there instead. Again, you can compare this to an F distribution to make a judgment of these linear combination, a judgment regarding the linear combination of the mu's. There are a variety of different matrices that might be of interest to you in terms of the h's to form these linear linear combinations of the mu's. In particular, you could set up an H to allow you to test for linear trend or quadratic trend. If you've taken Stat 802, you're familiar with that, doing that kind of stuff here. And it's basically the same kinds of matrices that you would do in 802 as you would here. Now, also in your very first stat course, you learned about doing a hypothesis test of, is mu1 equal to mu2? Is mu1 not equal to mu2? Meaning that you had, let's say, two different populations that you're taking samples from, and you want to compare the means. And if you remember, there was two different situations. You had independent samples or paired samples. Well, there are extensions of those same ideas to testing mean vectors. And again, it's based upon doing some stuff similar to like the Hotelling's t-squared. So if these are vectors then, there's a test statistic that you could use. You can compare it to the corresponding F distribution. That's for independent samples. You might remember, again, in your first stat course, you either talk about, can you assume that your variances are equal or not? If they're not, then or if they are equal, you can use a pooled estimate of your covariance matrix. If they're not, then you have to do some other stuff. There's the same extensions here. With paired samples, you do something very similar to what you did in your first stat course, and that is you simply took the difference between observations that are paired and essentially use a one-sample test. Okay? Then lastly all of you have seen analysis of variance, and the overall main thing that you do first with analysis of variance, if you think of just, let's say, a one-factor situation, you're testing, let's say, if you have m different treatments for a particular factor, you're testing, are all the means equal to one another versus not equal? Well, that's ANOVA. Well, you could simply replace those individual means with vectors of means, and now you have MANOVA, multivariate analysis of variance. There's a few different ways to go about then testing those hypotheses, and that's what I explain in these set of notes. And I actually then also give an actual example where to use this. This actually comes from a data set that I worked on when I had an internship as a student at a pharmaceutical company, and we were evaluating a particular new drug that was being developed. We were evaluating if it was safe to use or not. And this is a very common particular setting, not just in a pharmaceutical setting, but in other situations as well, where the data looks something like this, where you have a particular patient, let's say, and a particular dosage level given to that patient, and you want to look at, well, are there significant differences between the mean responses at the different dose levels? And so at time 0, our baseline measurement I get some kind of numerical value. At time 1, I get a numerical value, and I go all the way up to time 4, and I get a numerical value on the same patient. I do that for all the patients in this particular study. And then what you could do is, examine, are there differences among the, something like this. Let's say if I have a dosage level of 0, is that equal to a dosage level of 3? Is that equal to a dosage level of 9? And so on, and approach in this manner. And you can do that with MANOVA. That's the way a traditional way to handle the problem. Nowadays, there are other ways to handle these kinds of problems. Does anyone know how else you could deal with this? I know some of you have taken Stat 971. For those of you who have taken Stat 971, you should be, I'm sure Walt Stroop will be saying to you right now, you should know the answer. Did you ever talk about longitudinal data in Stat 971? This is longitudinal data. How would you model the responses here? Excuse me? Well, this is a repeated measure, yeah. So how would you model? What would be a particular kind of statistical model? Generalized, linear, mixed model. Thank you. A generalized linear mixed model. And the key that you have to understand here is that, we have this dependence across time in this particular setting. We have this dependence across time for what the responses would be. And so the traditional way that people would handle this would be to use like a MANOVA. But nowadays there are these things called generalized linear mixed models that allow you to better account for the covariance structure. I'll say better, sure. Allow you to count for this covariance structure that's within, let's say, the time levels. And so that's one particular reason why I don't think it's necessarily worth our time as much now as maybe it would have been 10 years ago to talk about a topic like this because of these generalized linear mixed models. I think that is all. Okay, are there any questions?
None of that's going to be on the exam.
Oh, it's all going to be on the exam. I'm joking. The testing mean section is not on the final. Unless you want it to be. It could be an extra credit problem.
That sounds all right.
Okay, so let's talk about the final exam. Again, 10 a.m. Tuesday here. It is comprehensive. However, there are no direct questions from the material in test number 1. What do I mean by that? Well, I will not ask you a question such as, what is the difference between using an asterisk and a percent, asterisk, percent with matrices in R? I will not ask you a question, what is an advantage to using 10R or RStudio for writing a program rather than using the program editor or writing in R? Well, remember, test number 1 was just basically background material. So, to some respect, you will be indirectly tested on it. I might ask you to, let's say, do some calculations, but I'm not going to ask you directly, what's the difference between an asterisk and a percent, asterisk, percent. So, is that clear? Any questions? There's also a format change to this final exam compared to other tests here. You will not be using the computer at your desk. Instead, what I've done to try to help you out is I've actually done all the computer work for you, and that will be given to you on the exam. Now, I might do the computer work in more than one way, and you need to know, well, which is the correct way. but I have done all the computer work for you. In fact, you don't even need a calculator for the exam. Yes?
How does this apply to the formula sheet with the one that you?
Well, I will still give you the formula sheet. I think of it more as a security blanket. You could think of it that way, that you've had this all throughout, and I don't find any harm in giving it to you again. Okay? So with respect to the formula sheet, I will actually pass out a paper copy since you won't be using the computers here. So, because, since you won't be even needing a calculator, there might be some places where I just simply ask you to show me how you would do something. Set up the calculations. You don't necessarily need to totally fulfill the numerical stuff. So, for example, like with the multinomial regression study, I might ask you, well, show me how you would find, let's say, pi hat 1, pi hat 2, pi hat 3, and tell me then how you would make a decision of which category to classify the observation into. Originally, I was going to have you all use a calculator for the exam, and then when I was looking at least the draft of the exam that I have done, when I was looking at it last night, I was like, there wasn't really that many places where you need to use a calculator anyway, so why don't we just, not do a calculator. Okay, so again, the test itself is not finalized. I have a good draft done, but it is not finalized yet. And this is what it looks like. First of all, it is a little bit longer than past tests. You have 2 hours to complete this exam, so it is a little bit longer, but not too much longer. I guess I would equate it to, let's say, a test. Well, let's say 1.3 tests in terms of length compared to what you've taken in the past. The first problem is something on multinomial regression. Since everything's not finalized, I'm not going to give you the exact point totals, but if you didn't study, if you decided not to study the stuff that we talked about this week, your grade would probably suffer. It is weighted enough that indeed, you should study the stuff that we did this week. So, number 1 is multinomial regression. Number 2 is over test number 2 material. Number 3 is I'm going to give you a data set, and you're going to do test 2 and test 3 stuff on it. Number 4 is some short answer questions. And number 5, an extra credit. So after I get done grading all the exams, I will post a message to the listserv saying, hey, I graded everything. I have put all your I have put all your grades on Blackboard. You can take a look at it. If you would like to see your final exam, please email me to set up an appointment. You can try just stopping by my office, but I cannot guarantee I will be there. It is finals week, and my schedule is not necessarily the same as it usually is. So I do recommend that you email me first to set up an appointment. You can take a look at the final exam. You cannot take the exam, though, out of my office. I do keep all final exams. Let's see what else. Okay. So that's the structure for the exam. In terms of reviewing for some material for the exam, basically all the test reviews that we've done before, I guess test number one's review is not that important, but all the test reviews that we've done before, I recommend just rewatching the video because I would basically tell you exactly the same thing here. So I'm not going to review that material unless you guys have questions on the material. With respect to the material that we've talked about since the last test, or wasn't on the last test, there was some stuff with respect to logistic regression. In particular, we stopped test number 3 material in the middle of the ROC curve section. So there was some stuff there that you do that is fair game for the final exam here. Of course, make sure you understand how to construct an ROC curve, understand sensitivity and specificities, and why the ROC curves can be so helpful. Make sure you understand how to construct an ROC curve. Think of it by hand. I think that's often, I know at least for me, when I was first learning about ROC curves, that was a difficult thing for me because, you basically, you're trying to find at a whole bunch of cutoff points, that's how you actually find the information that you plot. And so that's not necessarily intuitive when you first look at these ROC curves. Also, in particular, make sure you understand how to compare different ROC curves so that you can make a judgment about, well, which, let's say, model is better to use for classification. And if you remember, there was a few different things that we look at. For example, the area underneath the curve is a big one. But also, you have to weigh, sensitivity versus the false positive rate. Which is important to you, and then helps you decide on a place on the curve that to look at to allow you to compare different curves. So then, multinomial regression. Obviously, make sure you know how to state and estimate the model. Now, of course, you're not using R for the exam, so but you still need to understand how to read, let's say, R code that might be on the exam to understand if this is being done correctly. Also then, how to find pi sub j in terms of how to actually, let's say, estimate it, but also how to actually derive how pi sub j comes about with respect to how our model structure is. How to, once you have the estimates, how to use them then to make them the ultimate goal for us, which would be to classify observations. How to make that classification decision. Obviously, then after you make the classification, you would want to maybe look at some plots to determine where the model is working and where it's not. So you could do some PCA score plots. You could do parallel coordinates plots. Make sure you understand how to interpret them. And then similar to what we did at the end of the logistic regression section, make sure you understand how to summarize their accuracies in terms of, let's say, comparing different methods. We looked at those Trellis plots to make a judgment of, well, which method is best and so on. Okay, that's all I have for reviewing material. Do you guys have any questions?
So will proofreading code be a component of this, like recognizing errors in code, or just
I will not, let's say, give you a problem and say, tell me what's wrong with the code. But what I will do whenever I will give you, let's say, the R code that I use and some output. Maybe for example, I might let's think of it in terms of discriminant analysis. I give you maybe 2 different ways to use LDA, and I ask you to interpret the cross-validation results. So maybe I might do both resubstitution and cross-validation. You need to know, where to look correctly. Other questions? Well, if there's no other questions, then I guess that's it. I hope you feel as though you got a lot out of this course. I enjoyed teaching it. Like I said, it's been 8 years since I last taught this course. It was kind of fun going back to doing some old stuff that some of it I haven't done for a while, and to also learn how to do some of the stuff using R. R is statistics now, and it's only going to become even more important. Legacy software like SAS, SPSS, other software like that are increasingly becoming less important, especially as more and more graduates come out of universities. They're typically learning R a lot more than other software packages. So once that, and because that's happening, then these other the R is becoming more prevalent in industry and other applications as well. So it was a big undertaking to change all this stuff over to R, and I hope you have found it to be useful. If you have any questions before the final exam, please feel free to post them to the listserv. Okay, that's it for today.